everyone. Today we have our another new episode and we will discuss on quantum and versus classic. We have our world famous speaker, Mr. David Smith and Dr. Tamanna Khoshla. Mr. David, as you are Chief Technology Officer for iBeyond and you are doing excellent jobs with all of the quantum innovations. So my first question for you, what are the key difference between quantum mechanics and classical mechanics in terms of determinisms and probability?
Right, Dr. Shreve, great questions to start the program with. I will start a little bit higher level, then jump right into that question because you're looking at the difference between quantum and classical. Classical has several different iterations to kind of look at, but on the level of where your questions are today, classic mechanics, classic computing is probably like the computer you're using now, where they operate on bits, which are really basic units of information. So we've heard always that in classical, a bit can exist in one or two states, 0, 1s. And these bits are manipulated in the chips, the CPUs, using logic gates to perform various calculations and operations. And this binary system has underpinned everything we see in the type of computers we're using today, from simple uh, math to very complex data processing. And they've served us pretty well, but we have moving to a different form now of quantum. And quantum computing harnesses the principle of quantum mechanics. And this is what gets to the basics of part of your question there. In quantum, the basic unit of information is a quantum bit or a qubit. Uh, Unlike a classic bit, a quantum qubit can exist in a state of 0 or 1, just like classical, or it can exist in both states simultaneously. And this is called superposition. Uh, and the other thing is that in quantum mechanics, qubits can be entangled with one another. This means the state of one qubit can directly relate to the state of another, really almost no matter how far they are apart today. We're seeing this type of entanglement being done at more greater and greater distance. And this type of superpositioning, this type of entanglement really allows quantum to process and store an immense amount of information at once, which really is very different than classical. And some of the key differences and things to get in as we answer your question is in processing power. Quantum mechanics, quantum computers have the potential to solve very complex problems much faster than classical computings. And these include things like looking at encryption, factoring large numbers, simulating molecules and large systems. Uh, some of the other really interesting differences is that quantum computers are really highly sensitive to their environments, and they have a much higher error rate than classical computing. And we're seeing some breakthroughs in that area, which are really helping us deal with the error correction in the quantum environment. So if I go back to some of the classical computing, so classical mechanics is really deterministic, as you asked in your question. It means that the future behavior of the system really can be precisely predicted if we know the initial conditions and things. So if you look at that, we know the initial position and what's happening. We can pretty accurately calculate the future. And then probability in classic mechanics, it really typically arises from a lack of knowledge about the system. We can use it kind of to help track each things individually, but the underlying laws are still deterministic. In quantum, it's indeterministic. They introduce it into the description. So the exact outcome of the measurement cannot be predicted with certainty. And so like, for example, when you use quantum in a view to look at a molecule, it can describe it by a probability of distribution, but not a precise one, where probability is really intrinsic to quantum computing and is really looking at it's not due to lack of knowledge, but it's the inherent properties of quantum systems. And there's quite a few different principles in the different ones. One of them is Heisenberg's uncertainty principle, which is basically saying we can know certain pairs of properties simultaneously. And the more precise one property is known, the less precise the other can be known. And Heisenberg's rule of uncertainty is something that has been a problem when you begin looking at complex systems. And it's one which quantum mechanics really helps us understand much more. You also begin to see the superposition we talked about is there, and it lets us create interference patterns. The old classical thing many of us learned in college was the double slit experiment. And this quantum superpositioning helps us there, as well as the quantum entanglement we talked about before. So, and kind of to sum up on your first question here, classic mechanics, deterministic is where future states are really precisely predicted, where quantum mechanics are fundamentally indeterministic, but probability is an intrinsic feature to them. And so those are a couple of the big differences to answer your question, Dr. Sharif.
Excellent, Mr. David Smith. Dr. Tamanna, what you want to discuss about what are the key difference between quantum mechanism and classical mechanism in terms of determinism and probability? And if you want to add a few of your experience from academy from India. Can you unmute, please?
Yeah, so classical computing is generally largely it's used by large scale multi-purpose computer and devices. Quantum computing, on the other hand, is used by high speed quantum mechanics based computers. Then it's the information in the classical computing is stored in the bits. Information is stored in quantum bits in quantum computing. Then there is a discrete number of possible states, such as 0 or 1. But in quantum computing, there is infinite continuous number of possible states. Then calculations are deterministic, meaning repeating the same input results in the same output. But in quantum computing, calculations are problematic, meaning there are multiple possible outputs in the same input. Then the data processing is carried out by logic and in sequential order. But in quantum, it's like data processing is carried out by quantum logic at parallel instances. Operations are defined by Boolean algebra, as in classical computing. Operations are defined by linear algebra over Hilbert space amongst the quantum computing. Then circular behavior is defined by classical physics in classical computing, while circuit behavior is defined by quantum mechanics. So these are the basic difference between the two. Then I mean, if you look at the operating environments, classical computers are well suited for everyday use in normal conditions. Consider something as simple as standard laptop. Most people can use their computer out of their briefcase and use it in an air-conditioned cafe or porch during a sunny summer day. In these environments, for example, performance won't take a hit for normal use like web browsing and sending emails over a period of time. So, but I mean, as far as quantum computers are concerned, the need is to reside in heavily regulated and stringent physical environments. Some need to be kept at absolute zero, which is around 273.15 degrees Celsius. Although recently the first room temperature computer was developed by Quantum Brilliance. So these are the basic differences between several others which we can keep discussing over the period of time. But so obviously there is a lot of development, and I guess quantum computing is a development over classical uh, concept of computing, and organizations that don't plan on implementing quantum computing in their own business will still need to prepare for the external threats quantum computing might impose. So these things are not so easy, and just by making the distinction, we can't say that this is easier or that is easier. But we need to understand that both these computing are important and they can go side by side.
Mhm. Thank you. Mr. David, my next question for you. How does quantum superposition differ from the classical concept of states, and what implications does this have for computing?
Well, really, quantum superposition and the classic concept of states really differ in how they handle information and how they define the model of that information. And they have really some fundamental differences when it comes to the future of computing. And I'm treating your questions in both the physics of classic physics and quantum physics, as well as the principles of classic computing and quantum computing, because they intertwine so well together. So in binary states in classic computing, the bits are the basic information, units of information, like both of us said before. And each bit can be in only one of the two states, either 0 or 1. That is, they are exclusively a 0 or they exclusively a 1. And as we said before, that classic systems follow deterministic rules, where the next state of the system is really defined and determined by its current state, and then the operation that you're applying to it. That means that for a given input in this classic state, the output is predictable and is pretty easy to predict there, even though this can be complex problems. In quantum, though, the superpositioning, the qubits are the basic unit of information, like we said before. It's either exists in a state of 1 or a 0 or any quantum superposition of those states. And what this superpositioning means is a qubit can be in multiple states simultaneously until it's measured. And the state of a qubit is described by a wave function, which that's the easy way to describe that. This wave function combines the probability amplitudes of each of them being in each state. And when a qubit is in a superposition state, we get back to the probabilistic nature we talked about in the prior answer, it collapses to one of the possible states with a certain probability. And this probabilistic outcome is inherent in quantum mechanics and cannot be precisely predicted Where in classical computing, that the output is predictable. So that's a couple of the big differences. And what are some of the difference there? Quantum superposition is key, is really a key feature, I guess is the best way to describe it, uh, by quantum algorithms to achieve these fantastic, um, really exponential speed ups for what you can do with it. Um, if you begin to look at some of the benchmarks, things like Grove's algorithm and Schur's algorithm, uh, or Grove's unstructured search and Schur's is how to factorize, both of these really exploit the superposition capability to far outperform classic algorithms. And because of things like this, quantum can tackle problems involving vast amount of data and complex interaction that are really, for the most part, kind of infeasible today with classical approaches in classical computing. And so you begin to see things like, particularly in material science, pharmaceutical, and others, where quantum approaches and quantum computing have done things that would have taken a classical computing decades and decades to do. Uh, in cryptography, this is the encryption. Uh, Quantum has changed the rules in that area. Quantum algorithms can really break some of the most widely used classical encryption methods by factoring large numbers. Uh, However, now there are many quantum safe encryption methods that are being developed to address this area. And what's interesting is there's some efficiency to quantum computing versus classical, and reducing the time and energy that's required for certain computations. However, quantum computing with the other conditions around of maintaining the state where quantum computing works efficiently puts its own resources in it and its own complexity to it. And the fact that we are still working to put in place efficient error correction in quantum computing kind of gives you some ideas of where we the science needs to head to make this work efficiently in the future. So, Dr. Shreve, I hope that answers your question.
Thank you. Dr. Tamanna, what you want to discuss about these questions? How does quantum superpositions differ from the classical concept of states? Can you unmute, please? Can you unmute, please?
Yeah. Yeah. So, as far as quantum computing is concerned, like if you look at classical computing, while classical programs yield deterministic results, quantum programs work based on probabilities due to the nature of quantum mechanics. Qubits in superposition represents a range of possible states, and their probabilities collapse into specific result only when measured. This allows quantum computers to explore multiple solutions at once, making them ideal for tasks like pattern recognition. And like pattern recognition is something which is extremely important because, you know, even if it's a disease, for example, or it's like if we are looking at the galaxy, for example, a certain pattern, if you are able to recognize, it makes things much easier. So I guess and diagnosis etc of diseases etc would become much easier if patterns become recognizable, and that is why quantum programming is it obviously depends on probability, not certainty, but still there can be some amount of certainty because they're like looking at the patterns. That being said, it also needs repeated runs and statistical analysis to get accurate results. So it has to also demonstrate statistical analysis to get accurate results. Then quantum operations must be reversible, unlike classical ones. In classical computing, bits are transformed and information can be discarded during computations. Quantum computing, however, requires reversible operations to preserve quantum information throughout the process. This is crucial because reversing operations allow quantum systems to maintain coherence and take advantage of phenomena like superposition and entanglement. So yeah, and quantum mechanics, not classical physics, drives the process. Classical computer operates according to classical physics, describing predictable and deterministic behavior. On the other hand, quantum computing is based on quantum mechanics, which deals with the behavior of subatomic particles and involves concepts like superposition, entanglement, and quantum interference. As a result, quantum computers can perform tasks that classical systems cannot. So, that can be helpful in major discoveries. I mean, quantum mechanics can be of major help to doctors. It can be of major help to pharmaceutical industries. It can be of major help to astronauts. It could be a major help to people in university research, and that is what I like to say. Yeah.
Thank you. Thank you. My next question for Mr. David Smith. In what ways does quantum entanglements challenge classical notions of locality and causality?
Actually, once again, a good question, and particularly since this can be answered extremely technically, or I can do a higher level answer, which I think would help more of your audience than if we get into this one at the physics level, which is what it's really asking about in the question. So, kind of at the that level, let me break it down to key kind of concepts on the principle of locality. In classic physics and classic computing, um, there's the idea that interactions happen through local forces. Think of it like pushing a cart. You have to be right there in contact with it to make it move. And this is kind of ingrained in our understanding of how the world works. And Einstein's theory uh, that he proposed kind of reinforces this with equal and opposite reactions. And, you know, in Einstein's theory of special relativity, he reinforces this by saying that nothing can travel faster than the speed of light. And therefore, any influence from one point to another can be mediated by something traveling at or below that speed. Where in quantum, though, it's very different. Quantum entanglement really changes this whole concept of the localism of it. When two particles are entangled, their fates are intertwined, regardless of the distance that are separating them. So if you measure the properties of one of those entangled particles, the corresponding properties of the other particles become really instantly defined. And this type of correlation, going back to Einstein, is what he called I love this, a spooky action at a distance. Because quantum really fits his definitions that Einstein put around it being spooky. And it seems to suggest that there's some type of connection between these entangled particles that transcends the limitation of space and actually time we're beginning to see. And there's been many experiments and things that have validated over the years. And one of them, Bell's theorem, really shows it pretty well. And it basically shows that these coalitions between these entanglements cannot be explained by any locally hidden variable. And it just works there. Causality, on the other hand, in your question, in the classical world, uh, is the idea that every effect has a definite cause, and that causes always precedes their effects. And this is our really way how, if you look at classical computing and classical mechanics, it's our foundation of how events unfold in the world. However, in quantum, uh, entanglement doesn't necessarily break the cause effect rule in a way that we can understand easily, because this entanglement allows for sending signals faster than light. It allows for, in essence, time travel. And there's not a theorem that really explains that well yet. Quantum really, though, challenges our understanding of how causal relationships can exist. Um, and the cause and effect in the classical understanding is maybe sufficient to describe the quantum world, but there's still a lot of research, a lot of science that has to be done around that. And it's almost more accurate to say that entanglement displays non-local correlations rather than non-local causations, which is a weaker way of looking at it. And the couple of key things on this is the implementation of entanglement are still fiercely debated among physicists. One of my good friends, who's received the lifelong achievement awards from the Academy of Physics, basically says that there's so many different interpretation of quantum mechanics happening today that there is not a clear winner of the nuances of it. So it goes back to Einstein with the wicked, spooky problem there. There's a lot of ongoing research. They continue to explore this entanglement and how to transport it and the teleportation, everything to understand it. And quantum computing, quantum information science are really necessary as you look at where this entanglement can be used today and in the future going forward. So this is the difference between classical and quantum here really confronts us with how well we understand our science, how well we can understand the limitation of our classical view of the world. And as we go down further and further into this quantum world, how's that going to change the state, not of just computing, but how we see time and space, how we see dimensions, how we see other things like that happening within our world. And so it's a really fundamental question that there's not a solid answer yet.
Thank you. uh, Dr. Tamanna, how you want to explain this question? In what way does quantum entanglement challenge classical notions of locality and causality?
Yeah, so I guess one very unique thing about quantum computing is that it has a spiritual potential, which classical computing did not. That was just based on data and data collection, etc., those kind of things. But quantum computing harness the phenomena of quantum mechanics to process information in ways that quantum computers can't. So, where traditional computers use bits as the smallest unit of data, quantum computers use quantum bits or qubits, which can exist simultaneously as both 0 and 1. Now, what is this quantum and spiritual connection? At its core, quantum computing challenges our conventional notion of reality, much like spiritual practices have done for millennia. By leveraging properties like entanglement and uh, superposition, Quantum computing not only deepens our understanding of the physical universe, but also opens new avenues for considering how interconnectedness and energy influences our spiritual lives. So, how to bridging technology and mysticism. Firstly, understanding the universe. Quantum computing has the potential to unravel some of the most perplexing questions in science, such as the nature of dark matter or the origins of universe. There are questions that not only have scientific significance but also profound spiritual implications as they relate to creation and the cosmos grand design. Secondly, enhancing mindfulness practices. With its ability to solve complex problems, quantum computing could one day help optimize meditation, which is now the very in thing worldwide amongst the youth, for example, and mindfulness practices, tailoring them to individual psychological and physiological states, thus enhancing spiritual well being. Then it explores consciousness. Quantum computing could provide models that help us understand human consciousness, a subject that straddles the lines between neuroscience and spiritual science. Theories, spiritual experience. Theories positing that consciousness itself may have quantum roots could be explored with computational power of quantum computers, offering insight into the mind body spirit connection. And as we integrate more advanced technology into our daily lives, this potential spiritual application of quantum computing are vast. Imagine apps powered by quantum algorithms that help synchronize meditation sessions with natural energy flows, or platforms that connect thoughts and intentions across global conscious networks. So this could in fact connect people from different countries practicing meditation at the same time, and you just imagine the kind of vibration it's going to create in the world, and the peace which we require right now. Probably the answer would lie in the coming together of spirituality and quantum physics, quantum computing. So all of these together, a world which is high vibrational. I mean, I'm using spiritual words, maybe many people would not understand it, but many would. It basically requires that there should be a evil happens at level which is lower than your vibrations. When you have high vibrations, there is no chances of evil happening. So the world right now needs high vibration coming together, and peace to be established. And I guess quantum physics and computing, as well as spirituality together, can make the world a safer place.
Thank you. My next question for Mr. David. How does quantum computing exploit principles like superpositions and entanglements to achieve advantage over classical computing? Can we unmute, please?
Sorry. So quantum computing, like we talked about before, leverages the principles of superposition and entanglement to perform computation in a way that are totally fundamentally different and more powerful than what we see in classical computing. And just to make the point here, the classical computing and quantum computing both have their own place today. And it's not a either or, they really work in tandem. But kind of here's some of the details of the answer that you posed. In superpositioning, like we said before, quantum computing uses qubits, which can exist in a combination of 0 or 1, or 0 and 1 simultaneously in multiple states. And where classical computing uses bits, and they can only exist in a binary approach, that meaning they're either 0 or 1. And so that superposition is a very fundamental differences. And under when you look at them in the concepts of computing, and particularly large-scale computing, this quantum computer with the superpositioning allows it to explore many different possible solutions to a problem at the same time. And so if you have a number of qubits, they can represent the states, many different states simultaneously. So I'm trying to stay out of the details on this, but let's say you have an n qubit. They can be 2 times n at the same time. And it's this exponential growth in these states that give quantum computers their power and their speed to begin to look at a number of things simultaneously there. So a quantum computer can perform many calculations at once, where a classical computer would have to perform them sequentially. So much slower. Entanglement goes into one of the differences here as well too. And if I look at entangled qubits, entanglements where one or more qubits can be linked in a way like we talked about before, where their states, their fates are intertwined together. As we said earlier, measuring the state of one entangled qubit instantly determines the state of the other qubit, regardless of the distance and time between them. And what this does for computers, it allows for this type of entanglement, this type of quantum entanglement, allows for complex correlations between qubits, which can be used to perform computations that would be probably impossible for classical computing to do. It allows for the creation of very complex computational states that, when combined with this type of superposition, allows for extremely powerful algorithms, and for these powerful algorithms to maintain multiple processes together and with each other. And this type of entanglement is also vital for things like quantum communication. And we're seeing tremendous breakthroughs in science in quantum communications every few months. And the ability to do quantum entanglement and quantum teleportation has dramatically increased in the last year and a half. So how does this work in the world, in our real world today? So these principles you outline in this question, Sharif, really leads to what I think you're trying to point out is a quantum advantage. Superposition allows quantum computers to perform many calculations simultaneously, which dramatically increases power. This entanglement allows the creation of complex correlations and dependencies between qubits, which can be used to solve problems in ways that would take a lot of programming, a lot of computation in a classical computing. And you see that. And as we talked before, the use of these extremely advanced algorithms really works at greatly enhanced speeds over classical algorithms. And we've talked about a couple of others like Schur's algorithm and Grover's, which are ones that are differences there. So in essence, quantum computers uses the unique properties of the quantum world, the areas that Einstein, for example, described in his second theory and his theory of the extension to the theory of relativity, to perform computations in fundamentally different ways. than what you can with the classics. But just like Einstein said, though, a lot of how this works in the real world, a lot of this entanglement, a lot of the teleportation, a lot of the simultaneously states are still spooky problems that we're still working on every day to understand more and try to solve them, Dr. Shreve. So this is an area that uh, the answers are kind of like quantum answers. It's not black and white. There's still a lot of grays, just like quantum computing has a lot of grays when you look at the simultaneous states. We're still that in that same area when you look at the differences between quantum computing and classical computing.
Thank you. Dr. Tamanna, what you want to discuss about this? How does quantum computing exploit principles like superpositions and entanglements to achieve advantage over classical computing? Can you unmute, please?
I guess they're not really exploiting. I guess they're building upon what classical notion of computing was there earlier. And quantum technologies, for example, can solve problems of traditional computers which compute traditional computers could not. So I really don't think that they're exploiting it, but probably to learn a bit from them, their failures, their problems. And for example, the World Economic Forum quantum economic blueprint is a new guide for building a quantum economy. So new concepts are coming up, and I guess that's a major help to the world, and the growth of sciences as a discipline. And quantum technologies can transform whole industries, advance human society, and tackle some of the world's toughest challenges. They can also find solutions to problems that classical computers have not and may never solve. So, in a new report, the World Economic Forum set out a framework to build a quantum economy that is accessible to all nations and societies, developed responsibly and focused on economic growth and job creation. So, quantum economic blueprint has been published in the collaboration with technology companies like IBM and Sandbox AQ, an artificial intelligence and quantum technology company. So, quantum technologies are engineered on microscopic level by working with individual particles such as atoms, smallest building blocks of matter that make up everything around us, photons and electrons. So, this is all things. So why does quantum technology matter over classical technology? So the impact of quantum technologies will be far-reaching, with potential opportunities across multiple industries and advances in sectors such as healthcare, climate change, energy, communication, and finance. These innovations should be shared for the betterment of society, the sustainability of planet, and welfare of future generations. Making these technologies accessible to everyone will have a broad and long-lasting impact on the future of society. So, we need to understand what's the current state of quantum technology development. Quantum science and technology currently attracts around 40 billion dollars globally in research and innovation funding from the public sector. The number is continuously rising. Combined with artificial intelligence, quantum technology are already being used. For example, highly sensitive quantum sensors that drive key applications in medicine and navigation. So these are the whole thing. And so what about the quantum economic blueprint? The quantum economic blueprint starts with the guidance on how countries can develop a national quantum strategy. Next, it explores how to create broad access to quantum technology hardware and components, and to develop quantum technologies quickly and responsibly interoperability, the report says collaboration is key. Government, academia, and industry can also work together to raise awareness about quantum technologies, and it's a must. It should be used everywhere, especially in the developing world. Developed world has already used it, so we now it's our turn. And so this is what I like to say. Thank you, Dr. Sharif.
Thank you, Mr. David. My next question for you: why do classical systems obey Newtonian mechanism, while quantum system required wave functions and probability amplifiers to describe their behavior?
Like I say, part of the answer to your last question began to get into this. Let me break it down just a little bit further, because the answer to the difference between quantum and classical system really stems from the inherent nature of reality. And a lot of it, you have to look at the scale and the different scales which you're using. So in classical mechanics, the basic Newtonian type of classical mechanics, it operates on the principle of determination. And if you look at that, if you know the initial position and velocity of an object, you can predict its future trajectory. Same thing as you look at forecasts, and these are linear type of forecasts. If I know the multiple data points, I can begin to plot across those data points, and I can do a determination of what its future positioning is going to be. And this view really assumes that there's a definitive property of these operations at all times. And so classical mechanics, in classical computing, primarily treats objects that are well defined, and you understand their probability of where they're going. The law of motion, for example, describes how these particles would interact and move through space. With quantum mechanics, though, and again, we're moving back and forth between the physics of classical and quantum versus applications in computing. Quantum mechanics, like we talked about earlier, really is probabilistic, and it has a probabilistic view of reality. Instead of defined positions and momentum and where things are going, quantum objects are described by wave functions, which really gives you probability amplitudes. And this probability that when you square it gives the probability of finding a particle, a data point, and other things really in a particular location. And in wave particle theory, there's a duality. And quantum objects exhibit this wave particle duality. And what that means is that they can behave both as waves and as particles. And so that's where quantum is very different than classical in the answer here. And this wave-like nature is described by a different set of functionality than you would see in classical approaches. And I mentioned before the Heisenberg principle and the Heisenberg effect. And the Heisenberg uncertainty principle states it's impossible to know simultaneously both the precise location and momentum of a quantum particle. And this type of uncertainty in quantum is because of the wave-like nature of the quantum objects. And I know this is more of a physics type of answer, but your question really forces you to get into it at this level. And it's really hard for most business folks, many academicians to understand. So Why do you have the difference? And like I said at the start of this answer, part of it's because of scale. Uh, Classic mechanics are very good for looking at small objects and where the quantum effects can be understood. And at very large scale and at extremely small scale, uh, at the atomic and subatomic level, at the small scale, that's where quantum effects become dominant, and classical mechanics really breaks down there. Um, and it changes the fundamental nature of reality in some ways when you look at the differences between quantum and uh, classical, again, particularly talking about mechanics in the physics sense versus computation. Because quantum mechanics says that uh, the underlying nature of reality is probabilistic and wave-like, where classic mechanics basically says that the emergent property of quantum mechanics is only valid in places where the quantum effects average out. And the precision is not needed there. And, you know, one of the gaps that is uh, hard to put in our own minds is the one of measurement. In quantum systems, um, measurement is affects the system. Where in classical system, measurement does not typically change the state of the object being measured, but in quantum it does. And again, I'm going back to the spookiness of this is that this is one of the places where you begin to see that it is spooky and why quantum and classical mechanics and quantum and classical computing are much more difficult beasts to understand, particularly when you get down to the level, Dr. Sharif, where you're asking the questions today, because it takes you into the science and the physics of both of these systems, and that's where it gets very complicated. So, Dr. Sharif, I hope this answer was at a level that makes sense.
Thank you. Thank you. Yes, sure. Dr. Tamanna, what you want to discuss about why do classical system obey Newtonian mechanism? What you want to say about this question?
Yeah, so I guess Newton's concept was obviously revolutionary at the time of time when it came into being, and it developed into different streams. I mean, it has been used in many different disciplines, for example. Now, if you look at classical computation is rooted in what can be done mechanically. David Hilbert, for example, posed 23 math problem, and so it was like if it was to find an algorithm for diaphanite equation. Turing 1936 worked on 10 on computable numbers. So this way it did happen. So it was classical computing, for example, was called the church turning thesis. All computers are created equal, a hypothesis on the nature of computable functions. So I guess this is the whole thing. And if you look at classical computing, it is based on binary bit, while quantum is based on qubit. Parallelism, if you look at classical, is based on sequential processing, while quantum is based on massive parallelism through superposition. Hardware silicon chips at room temperature, while cryogenic quantum processor at the quantum computing level. So these things are there, but what I'm trying to say is that Newtonian concept has been used by both of them, and it is going to be needed for further development of computing age. And I guess in healthcare advancement, for example, precision modeling of protein folding mechanism, gene sequencing, disease pathology simulations, personalized medicine and drug discovery can transform healthcare and life science through quantum computing. Now, if you look at climate change science, NASA plans to use quantum computing for very high resolution, regional and global scale climate modeling by assimilating large data sets using quantum neural network. So many of these things are there, and artificial intelligence and machine learning, if it were to be looked at, quantum computers have potential to accelerate or improve machine learning relative to classical performance. It harnesses statistical distribution to tackle machine learning problems efficiently. So what I'm trying to say is, since the time of Newton, a lot of developments have come, but we still need to look back to him. But we have many more scientists who have worked on it, and the need for example, as I was talking about spiritualism, so different streams coming together and working together on quantum physics and classical computing would lead to a developed system of computers which would be able to answer questions which have hitherto not been answered. Thank you.
Thank you. Thank you. Mr. David, what's your closing remarks for today's session?
Dr. Sharif, thank you. Your session today has really made me have to sit back and think through my physics and my other backgrounds that are really important to understand topics like this, and more than where the application space lies and what we can do with it. Uh, so I guess in closing is both of us have talked about the transition from a classical mechanics and a classical computing environment to one of quantum mechanics and quantum computing really marks a profound shift in not only our understanding of computing, but our understanding of the universe. Quantum physics, with its deterministic laws and intuitive notions of locality, really is great for looking at a microscopic view of the way we do things. And the classical computing really does this in a way because we know it's either a 0 or a 1 and not in multiple states. And we can use that to construct more simplistic programs and more simplistic algorithms in helping to do things. So it's in the quantum world, it's as we said before, it's very different with the superposition, the entanglement, how the quantum world is governed by probability and by this wave particle duality that we talked about. And the duality and the entanglement and the superposition all go into making what makes quantum computing more powerful, what makes quantum mechanics more powerful, but also much harder to understand. And like I said, we're still in the stages of science trying to understand that. So some of my key takeaways I think we've talked about today is that scale matters. And we see the differences in quantum computing and classical computing and quantum mechanics and classical mechanics across all of these. That determination versus probability, where classical physics, in classical computing, we can predict the outcome with some degree of certainty, where quantum mechanics is probabilistic, really providing only the likelihood of outcomes. We talked about local versus non-local. Classic computing, classic physics adheres to locality, where quantum entanglement really demonstrates a non-local correlation. And this non-local correlation is where we see us questioning and us challenging our understanding of space and time, and even dimensions. Part of it, as you look at Einstein's extensions to his work, this whole concept of multi-dimensioning comes through this really view of local versus non-locality. And again, you see the same thing with certainty versus uncertainty between classical and quantum. And it begins to see it. Measurements different, but like I said, one of the big differences also is this wave particle duality, where quantum exhibits both wave-like and particle-like behavior. And this ability to have this duality is really totally foreign to the concept of classical physics and classical computing. So those are a lot of the difference there. And we're still continuing to explain and explore deeply the science of this quantum realm. And we're really likely to uncover deeper insights to particularly the nature of reality. And as we begin to understand these dualities and the superposition and the teleportation, those are the things that are going to stretch our science in this area considerably, Dr. Sharif, over the next decade.
Thank you, Mr. David Smith, and thank you, Dr. Tamanna, for joining today's sessions. I request all of our audience, please share our content as much as possible. And we are doing our research, our innovations, and this kind of dialogues for uplifting the emerging economy, the global south. Definitely, we need more partnership and collaborations with Global North, and definitely Mr. David Smith always support World Talent Economic Forum. Tamanna also very helpful for World Talent Economic Forum. And beside that, IBION has innovations and their own technology which can helpful for emerging economy. So we are working together to grow digital economy for Bangladesh, for India. Thank you everyone for joining today's sessions. I request all of our audience, please share our content as much as possible and share our good information with the government agency, corporation, and academia. Thank you. Bye-bye and take care.